Hello friends, welcome to another video in digital system design. We'll talk about fault detection and location in combinational circuits today. This is more of a theoretical introduction to this topic, so let's get started. The definition of fault is the first thing that we need to look at. It's a physical defect or imperfection that occurs between some hardware and software components. So most likely the faults are going to happen at the interconnections of the gates or the components. Now, there are different fault models, and these models are based upon the nature of the fault, the value of the fault, extent or duration. We'll talk about all these in details. Now if we talk about the fault models based upon nature, they can be categorized into logical and non-logical fault models, and logical fault models are of two types: stuck at 1 and stuck at 0. Okay, let's look at stuck at 0 fault. For example, we have this gate and we have these two connections, and these connections represent input A and B. Now if for some reason A is stuck at 1, even if we are making A 0, it is not giving a 0 input to the gate. So if A is stuck at 1 for some reason, now if for some reason A is not changing its value and it is stuck at 1, it will be known as stuck at 1 fault. Even if we give a 0 at the input, it would not give a 0 at the gate. So that's known as a stuck at 0 or a stuck at 1. And then we have the fault model based upon the value. This fault model suggests that the output of the combinational circuit is stuck at some value. For example, if Z is stuck at 0, even if we are changing the values of A and B, it is not changing. Z is not changing, the output is not changing, then it is a fault model which is based upon value. So value corresponds to the output if output is stuck at something. However, stuck at 0 and stuck at 1 faults are representative of the logic levels stuck at the inputs. Then we have the fault models based upon the extent. By extent we mean that if the effect of the fault is going to be local or is it going to be distributed. For example, if you encounter a fault here, or as a matter of fact at the output of this gate you encounter a fault, then it is most likely to propagate further in the combinational circuit, causing a fault here also. But if you encounter a fault at the output here, it will be a local fault because it will not affect the other part of the combinational circuit. So this area could crop up a distributed fault and this area could crop up a local fault. Then we have the fault models based upon duration. So we have temporary and permanent. Now these kind of errors are due to gate delays and are difficult to locate. For example, if we give a 1 1 1 here, the output could be 1 because a 1 and a 1 could give me a 1 here, and a 1 and a 1 a 1 and a 0 would give me a 0 here, and finally we get a 1. But if this 1 changes to 0, then for some delay of this NOT gate will cause some delay in the transitioning of a 1 here, and for some time it will change to 0, and this is explained very well in my other video, which are static hazards. If you want to see the condition where you get this kind of a scenario when one input is going directly into one gate and its inverted is going into another, that causes a static error, stuck at 0 and stuck at 1. So you could look that, but you can understand while transitioning, this 1 will temporarily go to 0 and then will become 1 again. So this kind of an error is temporary in duration, but nevertheless it's a fault. And then we have permanent nature of fault models, which are more likely to occur at points where the error will result in a permanently disabled or debilitated output. So these are the fault models. They are based upon different parameters, and you could learn them from the perspective of the theoretical examination. And I'll see you around with some more numericals on these fault models. Till then, take care. Bye bye.